Hey everybody, welcome again. This is Steven from LearnCMM.com and Victory Programming. We're going to go over some more awesome Calypso tips. I'm going to share my screen here. And today our topic is going to be about working with small grooves and also part variation on shallow features. How do you get those to work without crashing when there's part variation? So first of all, I'd like to look at this part where we have this shallow pocket in here. And this is not very deep compared to the rest of the part. So if I take a point on there, you'll notice our probe ball is relatively small compared to that depth. And sometimes you're dealing with features where the depth is like half of the probe ball or equal to the probe radius. So you really want to be able to catch that surface without it slipping off. So one trick is to reference the other face or the depth of that surface and then use that as an alignment origin or possibly a formula. So I'll show you both ways. So let's say we're already getting this surface. We're getting the depth of this surface with a plane. And then we need to reference that z level of that plane. It's minus 0.118 in inches. So I'm going to delete these 2 points. Actually, just one of the points. So if I go and I want to get a line on this surface, let's say we're trying to get the angle there and we need to measure a line right here. So we get 2 points. And how do we set that, the height of that line relative to the plane on the bottom of the pocket? So first of all, I'm going to set the angle of this line so that it's not tilted relative to Z. And it's 10 degrees relative to XY. So now, one way I mentioned, you can do a formula in this box. So in a lot of the Calypso dialogues in the boxes, you can enter a formula that references other features and can be really powerful. So you just right click on the box and click formula. And then in here, you can choose in the middle list which features you're referencing. So we're going off of plane 2, and we want to use the Z value of that plane 2. So we double click this. So we're getting the actual of plane 2, the Z value. And we want to go up a certain amount. So we have a 2 millimeter probe ball here. So in inches, that's going to be approximately 40 thousandths radius. So at a bare minimum, we need to go 40 thousandths up from that surface. So we type plus 0.04. You do need to have the 0 before the decimal, otherwise it won't work. But I don't want to go that close. I want to leave a little bit of room. So I'm going to go 0.05 and then OK. So that's going to set the height of my line with about 10 thousandths of clearance or space there. And like I said, sometimes your pockets are really shallow, so you need to adjust from there. And you can go back in there if you want to increase it at all. So that's your formula approach. There are times where the formula is not ideal. I recently did a job where we wanted to change the whole program to metric from inches or vice versa, because the machinist needed to see in inches and the drawing was in metric, things like that. The problem is with the formula here, it's not going to directly convert any of these values. So if you're running into those issues, you can just do a secondary alignment instead. It's about the same number of steps. And it accomplishes the same thing. So we're going to create a secondary alignment. I have a shortcut here, but you can do go to Resources, Utilities, and Alignment. That will create a secondary alignment. It looks a lot like a regular base alignment window. And in here, we're not going to fill in. All right. Let's see here. Looks like we had some disconnection. Thanks, Jonathan. We're back. I have no idea what's going on. In the past, this was working just fine. So cross our fingers. Hopefully we can carry on. So I'm going to rewind a little bit. Hopefully we can cover back to what we were talking about. Okay, so we already talked about the depth feature, using the formula, using the Z origin on the pocket. So I think what we missed on that during that time when we had a disconnect, we're going into a groove. Okay, so what do we need to think about when we're dealing with a groove? So first of all, I'm going to take a symmetry point, one on each a point on each side using the define points. And then that way I can get the width of the groove right there. I can click the distance. I got the groove width. And you'll notice these points are not exactly across from each other, which is not really a huge issue. But what you can do, if you're an inspector like me, you want things just perfect, you can go to Strategy and then double click the probing points. And here you can set the coordinates to be 0 so that they're straight across. Now here it's showing the coordinates relative to the element or the feature itself, which each feature has its own orientation and origin type of thing, which can be a little bit confusing, but here we're just looking for the ones that are slightly off. These would be the coordinates relative to the center. So you can kind of ignore the XYZ. We'll just set these 0, 0, 0. And now that point, symmetry point, has points on opposite sides of each other. Okay. So now, even though this groove is kind of large compared to the balls, we're going to pretend it's pretty tight. And when that is the case, you need to make sure your retract distance is not too much. So you go to Strategy and then Clearance Data. And right here, retract distance. So the default I have set here is 1 millimeter, 40 thousandths, but you can uncheck this and override it. So if I'm dealing with a tight groove, let's say the groove is only 90 thousandths wide and my probe is 2 millimeters. So I only have 10 thousandths to work with. That's pretty tight. So I might go 0.005. You wouldn't want to go to all the way to 0 because there is going to be a little bit of variation in where that surface is. Okay. So typically, when I'm dealing with a groove that's tight, I'll just take the groove width minus the probe ball diameter and divide that by 2. So if your groove is, let's say it's 3 millimeters, and your probe ball is 2 millimeters, that gives you 1 millimeter of gap. And so I would put my retract at 0.5. Same goes for holes. You can use that same formula. So setting your retract distance is important in this case. What else? When you're dealing with small grooves, there's part variation. Again, similar to the Z origin on the pocket, one thing we might do is set a local XY origin so that that probe can get in there precisely even if the entire groove is shifted. So what I mean by that is we would take a a point that is not in the groove, but somewhere near. So let's say we do a point here to set a local X origin, and then somewhere else we might set an origin. In fact, let's just say that this entire groove and these holes are machined in one operation, and all that might be shifted relative to the outside of the part. So we're going to do a circle on this hole, because that hole and the groove, it's all in one operation. It's all pretty tight. But everything in the central area might be shifted relative to the outside because maybe it's a casting. So we've got that circle, and then we're going to set another secondary alignment, and that's going to be off of that circle. So our X and Y coming off of that circle. And there we go. So that's our local alignment for this operation. And then when we have our symmetry point, we'll drag that below it because it depends on circle 1 for the alignment. So we're going to go referencing alignment 1. So now anytime we measure this symmetry point for the groove width, it needs to measure the circle first to set the XY origin. And then you'll notice these coordinates, X and Y, are coming from that circle. So if that whole area is shifted, it's going to follow along with the circle. You would do this most often like with castings or plastic parts. You need more local origins to adjust for warpage or variation, especially with plastic. Okay, you guys have any other questions? If not, we're going to just carry on talking about dealing with part variation. Another scenario you might run into is where there's a lot of part variation, like not just a millimeter, but maybe a 1/4 inch or a 1/2 inch, because maybe that surface doesn't have any specific alignment. Again, maybe it's a casting, maybe there's like extra gate material, things like that. It's not very often, but you may see that. So let's talk about that scenario. So we'll say this plane is our plane with large variation. It may be a z value of 1.1. It may be a z value of 1.4. It's just because of the process, for some reason, it's all over the place. So if you're dealing with lots of variation, you can set the retract distance to be higher. Let's just put in some points here. So you could say my retract distance is going to be 1/2 inch, and it will come 1/2 inch away from where the probe will come 1/2 inch away from where it should be, and then it's going to go and take a point. But with large variation like this, it may crash because Calypso is expecting, not that much deviation from the nominal surface. So the way to get around that is you'll go into your measurement plan editor, and then you'll do probing. So under the main menu, you go to probing, and then you do search distance before nominal position. So the first option here. And right now it's all grayed out because it's going by the defaults for the entire program, but we're going to use the second option to set individual features. And we're going to select that one and go put in a 1/2 inch. So what's going to happen is the probe will come 1/2 inch away from the part, and it's going to drive slower than normal, searching for that surface. So it's allowing for a lot more variation. It's expecting the surface to be off anywhere within that range. the search distance after nominal, the default is quite a bit. I think it's like 10 millimeters or something. But again, you can set this to be something specific. 0.5. And there you go. So those are the two things I would set. And you can use these search distance settings also if you want to make a extra smart program that is accommodating any variation in the fixturing. So for example, if you have a part that is really tricky to fixture and you can't really locate it very well, you can just put it in an approximate location, have some, rough alignment points like for circle and top plane, and have a large setting for the search distance. And that way the probe can basically find it. Okay, inspector T. Most programs I noticed clearance distance is set to 0. When would you need to set it to something else other than 0? Awesome question. So clearance and retract distance, it's always confusing to new people, and it's because of the naming. Because when you're thinking of clearance, you're thinking of the distance away from the surface, and same thing with retract. So they're kind of seem like the same thing. But so what's going on here is you can have your entire program with a clearance distance of 0 and it will run fine, because the retract distance will be used as the first clearance before the first point. So let's talk about what is the difference. Okay, so the easiest one to understand is the retract. So I'm going to simulate this really quick just so we can get an idea what is the difference. So we'll just do it on this top plane to begin with, and I'm going to set this higher. So it's going to retract 0.2 inches. And we're going to just run this one feature. I'm going to turn on the trailing path. So you'll notice it's kind of going fast, but it took the points and it jumped up 0.2 inches between the points. Let's just run this one more time. So the probe is going to go up 0.2 inches and in between each point. So that's your retract. Pretty straightforward. That makes sense. What about clearance distance? Okay, and here you'll notice the clearance distance was 0. Let's set that to 1 inch, okay? And let's see what happens in that case. Execute now. So boom, 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 boom. It didn't seem to be any different. Okay, so what's the deal? You'll notice that our clearance plane is 0.3, 0.39. So let's move that up so we can possibly see a difference. So go 2 inches up, and we'll go back to this plane. Okay, so our Z clearance plane is 2 inches above, and still we're not seeing a huge difference because the clearance distance in the simulator is not showing the brief pause, but it's almost not even a pause. So the clearance distance is the distance before and after the first point or scan in the normal direction of that feature. So on a plane, it's almost the same thing as the retract distance. It only happens before and after. And on a cylinder, it's different. On a circle, it's different. So that's where you're going to see more of a difference here. So let's talk about clearance distance on this circle. So we'll reenact this with similar scenario. We'll start with a 0 and we'll go from there. Okay, so let's execute this one. The probe is going to come down from our clearance plane. It's going to go in there and scan, come away the retract distance. That was the 100 thousandths. And then it's going to dive up. Now, what happens if we turn on a clearance distance? Let's say we go 1/2 inch. Okay, try this again. Just going to scan. And again, we don't see much difference because the probe is measuring in the same normal direction as the feature. So that clearance distance, it's almost invisible. But I'll show you where the clearance distance is actually useful. And bear with me, this can be tricky. So let's say I'm going to grab a different probe here, like a star probe type of thing. Let's say I'm measuring these side cylinders, but for some reason or another, I have to use the Z clearance plane and then dive in. I can't come from the X clearance plane. So I'm going to take a circle off of there. And if we set it to Z and our clearance is 0, you'll see how it will crash. So we execute this. It's going to come down and it's going to crash right into the part. So it's going right through the surface. And this is where the crash happens. So in this scenario, what we need to do is use a clearance that is coming out of the surface. So this is a 1/2 inch from that scan path. And we're going to execute that again. So you'll notice it comes and it clears that cylinder before it dives in and does a retract distance. So here we have that this is our 1 millimeter retract. This is our 1/2 inch clearance distance. And there we have our move to the clearance plane. So in summary, clearance distance is good when you're trying to measure a cylinder and you're approaching from a non-standard direction, or if you have a hole that's at an angle and your probe needs to come down and then dive in. I do have a video on my channel about this. It kind of goes over similar explanations, but check that out. It explains the difference, with a simulation example. But hopefully that clarifies to you the difference and why you need clearance distance in some cases. I actually do set most of the time the clearance distance to 0 and just handle the real clearance or the retract just with the retract distance. All right, we are out of time for today. So another thing I want to mention, every Monday we've been doing a private group Zoom training for 1 hour. So if you're interested in that, just email me, steven@learncmm.com, and we'll get you set up with that. So you guys have a great rest of your week. I hope you do well at your work and have a great day. Thanks.